I've always been drawn to stories that put our intellect, and our hubris, in perspective. There's something profoundly humbling about a narrative that reminds us that, despite our technological marvels and scientific achievements, our grasp of the universe is still quite limited. The tale I'm about to share does exactly that. It invites us to ponder our cosmic insignificance and challenges our long-held beliefs about the nature of reality. Imagine for a moment that awe-inspiring telescope we built, a technological marvel that has given us snapshots of distant galaxies and nebulae that stretch the limits of human imagination. Now, envision yourself floating in an endless void, where the nearest sign of life is not merely a few light years away, but billions of them distant. This isn't a scene plucked from a futuristic novel, it's a potential reality that modern astronomy is beginning to unravel. Recent astronomical observations have led scientists to a startling hypothesis: our Milky Way might be situated near the heart of an enormous cosmic void, a region of space spanning roughly 2 billion light-years. This revelation is more than a curious anomaly, it forces us to rethink the foundational assumptions of cosmology. For decades, our models have relied on the belief that matter is spread relatively uniformly across the cosmos. Yet, the existence of such a vast underpopulated region directly challenges this notion, potentially altering our understanding of the entire universe. Historically, the cosmic microwave background, CMB, the faint afterglow of the Big Bang, has been interpreted as evidence for a nearly homogeneous distribution of matter across space. This uniformity is a central pillar of the cosmological principle, which suggests that the universe is the same in every direction when viewed on a sufficiently large scale. However, the discovery of this massive void, sometimes referred to as the local hole, suggests that our cosmic neighborhood might be more uneven than previously assumed. Initially, the idea of an enormous void surrounding our galaxy was met with skepticism. After all, if the CMB indicated a smooth and even cosmos, how could such a dramatic gap exist? Yet, as astronomical instruments and observational techniques have become increasingly sophisticated, the evidence in favor of the void has grown harder to ignore. Detailed surveys of galactic clusters and the motions of distant galaxies have revealed irregularities, a significant paucity of galaxies and unexpected velocity patterns in certain regions, indicating that we are indeed in a remarkably empty part of the universe. What makes this discovery even more compelling is its potential connection to one of modern cosmology's most persistent puzzles, the Hubble tension. This term refers to the discrepancy between the universe's expansion rate as measured by local observations, like the movement of nearby galaxies, and the expansion rate inferred from the CMB data under the standard cosmological model. In regions dominated by a vast void, galaxies appear to recede from us more quickly than those situated in denser areas. This suggests that our location within this cosmic chasm might be skewing our measurements of the universe's overall expansion. One intriguing explanation for this phenomenon involves the concept of gravitational outflows. In essence, the low-density nature of the void might allow the gravitational influence from the surrounding, denser regions to pull matter away from the void. This siphoning effect could cause an acceleration in the local expansion rate, making it seem as though space is stretching faster in our vicinity. Such a mechanism hints at a radical possibility: gravity might behave differently in the emptiness of a void than it does in regions where matter is concentrated. These insights lead us to a profound question: is our entire understanding of cosmic expansion, and perhaps even the structure of the universe itself, being influenced by our peculiar position within an enormous void? If the conventional models, which assume a uniform distribution of matter, are off the mark, then many of our core cosmological theories might require significant revision. The idea that we are living in a giant underdense region adds a new, unexpected twist to our cosmic narrative, challenging the prevailing assumptions of the Big Bang theory and the standard model of cosmology. Consider for a moment the implications of this possibility. If the expansion rate of the universe varies with location, one must ask whether the Big Bang was truly a singular, all-encompassing event. Perhaps, instead, it was a more localized phenomenon, one that might be interpreted as an echo of far more intricate and varied processes occurring across the cosmos. This line of thinking opens up entirely new avenues for exploring the dynamics of cosmic evolution and forces us to question what we really know about the early universe. Recent studies have delved deeper into this conundrum. For example, research published in the monthly notices of the Royal Astronomical Society by Indranil Ban has presented compelling arguments linking the existence of a massive cosmic void to the observed discrepancies in the Hubble constant. Ban's work suggests that the gravitational effects within such a void, along with the resulting peculiar velocities of galaxies, could be artificially inflating our local measurements of the universe's expansion rate. In doing so, his research challenges the traditional assumptions of a uniformly expanding cosmos and invites us to consider the influence of large-scale cosmic structures on fundamental cosmological parameters. Another fascinating aspect of this research involves the exploration of modified theories of gravity. Traditionally, the unexpected rotation speeds of galaxies have been explained by invoking dark matter, an unseen substance that supposedly makes up most of the universe's mass. However, some scientists propose that these anomalies might instead be explained by adjustments to Newton's laws of gravity when applied to regions with extremely weak gravitational fields, such as those found in cosmic voids. If these modified dynamics are correct, they could undermine the very foundations of general relativity and prompt a re-evaluation of our understanding of both dark matter and dark energy. This possibility extends beyond just galaxy rotation curves. For instance, consider the massive galaxy cluster known as El Gordo, whose properties have long baffled astronomers because they do not fit neatly within standard cosmological predictions. The extreme behavior of such clusters could be a natural consequence of residing near or within vast voids, places where the usual rules of cosmic structure formation might not apply. In these regions, the interplay between gravitational forces and the distribution of matter may lead to phenomena that challenge our established models of cosmic evolution. One of the more intriguing questions raised by these findings is how the absence of mass in a cosmic void might affect the curvature of spacetime itself. According to general relativity, mass and energy warp spacetime, and this curvature dictates the motion of objects within that space. However, in an expanse where mass is notably scarce, the traditional equations might need to be adjusted. Emerging data suggest that these colossal voids could exert a far more profound influence on the universe's overall geometry than previously thought, possibly revealing hidden or poorly understood aspects of spacetime that only become apparent under such extreme conditions. Moreover, these cosmic voids force us to confront the complexities of the early universe. The theory of cosmic inflation, a period of rapid expansion shortly after the Big Bang, posits that tiny quantum fluctuations were stretched to astronomical sizes, leading to the formation of large-scale structures in the universe. This process was thought to smooth out any initial irregularities, creating a uniform cosmos. Yet, the presence of enormous voids indicates that this smoothing may not have been entirely even. In some regions, the inflationary dynamics could have been disrupted or varied, leading to unexpected differences in the distribution of matter on a cosmic scale. In this context, cosmic voids become natural laboratories for studying fundamental astrophysical phenomena. For example, gravitational lensing, the bending of light as it passes near massive objects, is significantly influenced by the distribution of matter along its path. In the case of a void, where there is a stark absence of mass, the way light is deflected can provide valuable insights into the behavior of dark matter and dark energy. Since these mysterious components make up the majority of the universe's mass-energy content yet remain invisible to direct observation, studying the lensing effects around voids can help us piece together their elusive nature. The implications of living in a cosmic void extend beyond mere academic curiosity. They force us to reconsider our place in the universe on both a scientific and philosophical level. If vast regions of empty space separate clusters of galaxies and pockets of cosmic activity, then the emergence of life, and the development of complex civilizations, might be far rarer than we once imagined. In a universe where habitable zones are few and far between, our own existence becomes even more remarkable and isolated. This realization challenges long-held assumptions about the universality of life and raises important questions about the prospects for interstellar communication and travel. If the cosmos is a patchwork of densely populated regions interspersed with vast voids, then the odds of encountering other advanced civilizations may be much lower than hoped. Such a scenario not only reshapes our understanding of cosmic habitability but also forces us to grapple with profound existential questions about our significance in an immense, indifferent universe. At the heart of this entire discussion is the fundamental nature of cosmic structure itself. The discovery of enormous voids compels us to re-evaluate the core principles of modern cosmology, the belief in a homogeneous and isotropic universe. Instead, we are presented with a picture of the cosmos that is both dynamic and intricate, where the distribution of matter is far more complex than our simplified models suggest. This realization underscores the limitations of our current observational frameworks and highlights the need for new physics that can accommodate these anomalies. The work of researchers like Ban, who explore the interplay between cosmic voids, gravitational dynamics, and the Hubble tension, is at the forefront of this paradigm shift. Their studies not only challenge conventional theories but also open the door to alternative explanations that could eventually revolutionize our understanding of the universe's true expansion rate. Whether through modified Newtonian dynamics or entirely new models of gravity, the quest to comprehend the influence of these vast empty spaces is reshaping the landscape of astrophysics. In summary, the notion that our Milky Way might be located near the center of a colossal cosmic void is more than a mere curiosity, it is a challenge to the very foundations of cosmology. This discovery forces us to re-examine our assumptions about the uniformity of the universe, the behavior of gravity in low-density regions, and even the origins of cosmic structure itself. As we probe deeper into these vast emptinesses, we are compelled to ask not only how the universe expands, but why it does so in such a complex and uneven manner. The study of cosmic voids has far-reaching implications. It touches on everything from the dynamics of galaxy formation and the mysterious nature of dark matter and dark energy, to the very geometry of space-time as described by general relativity. It even has the power to alter our understanding of the Big Bang and the inflationary period that followed, suggesting that the early universe may have been more chaotic and varied than the smooth picture we have come to expect. As we continue to refine our observational techniques and push the boundaries of our theoretical models, the cosmic voids may eventually reveal secrets that challenge our most cherished ideas about the cosmos. Whether these findings lead to a minor adjustment in our models or a revolutionary overhaul of modern cosmology remains to be seen. What is clear, however, is that our journey toward a deeper understanding of the universe is far from over. In the end, the exploration of these vast, empty regions of space is a humbling reminder of our place in the cosmos. It underscores the fact that no matter how advanced our technology or how confident we are in our scientific theories, the universe always has surprises in store. The discovery of a massive cosmic void not only enriches our scientific knowledge but also invites us to reflect on our own existence and the intricate, often mysterious, fabric of reality.